Hello, welcome back. This is a lecture on review of basic probability notations and concepts. This is Professor Wu, and let's get started. So, we previously learned a lot of linear algebra, and we've learned that in linear algebra, we denote lowercase x as either a vector or a variable. And capital X, we denote it as a matrix or vectors of vectors. However, these symbols has very different meaning when we talk about them in probabilistic and statistic sense. Lowercase x in probability and statistics denotes one or multiple events that happened, past tense, something that happened. And capital X is a random event of many possible outcomes, and you don't know what happened yet. So capital X is some is a there possibility of events, but nothing has happened yet. Lowercase is when something already happened. Okay, and we either use capital P or lowercase p to represent the probability function. For example, you will see lowercase p probability that x, remember, lowercase x is that something happened, right? So probability that x happened given the events of capital X is 0.25. That's what that is saying. So it's 25%. Now, over here is another way of saying exactly the same thing with a capital B. The probability that X happen out of all the possibilities in capital X is 0.25. So these two things are basically saying the same thing. Most of the time, we prefer to use this notation since it's just shorthanded. Okay, so P of X is essentially, you can picture that as a function where you simply plug the event you care about. So, what is the event you care about? And it outputs the probability of that event happening. This function is called the probability mass or probability density function. Okay, so depending on the context, it could be probability mass or probability density. Okay, so the difference between probability mass and probability density is that probability mass are for discrete events, one, two, three, four, right? It doesn't have 1.5 or 1.7, whereas PDF are for data that are continuous, so time, for example, or distance. Example of probability mass function. Let's say we have a die, and we roll the die 5 times, and we got these results: 1, 1, 3, 4, 4. Okay, so based on this data, we can say that according to the data, the probability you will get a one would be 2 out of 5, right? Two out of 5. The probability you get a two, well, according to this, is 0. Probability you get a 3 is just 1 out of 5. Probability 5, since it didn't happen, we're going to say 0. Probability 6, it's 0 as well. So basically, this is an example of probability mass function because the events are discrete. Okay. Now, we can write it this way with capital P, or notice how it's just a lot shorter to write it shorthanded. Probability that 1 happened, probability 2 happened, right? Or you can write it this way, probability. So in this table, you're saying that the probability that X is equal to nuclear would be right around here. So 0.25, right? So, or you can write probability of nuclear. So that's an example of probability mass function. Probability density function, on the other hand, are for something that's continuous, meaning that if you have a function that models the probability, let's say you have P of X, the probability of daily time spent studying to achieve a higher grade. Well, so chances are to the higher grade that probability you spend a lot more time here and that very low probability that you didn't study at all. So this is an example of a continuous time, right? So With this probability, the way you want to find the probability of an event is to say, well, what is the probability that a person spent between 1.5 and 2, right? And you need to find the area of this portion. And we learned previously in calculus that when we find the area, we have to take an integral, something like this. So if we want to find the area between 1 and 2, right? 1 and 2, we would need to take the integral of our probability function to find that area. Okay? So, so this is an example of that. So right now, what I want you to do is see if you can find it. What is the probability x equal to 1? And then probability of x between 0 and 1, and probability of 0 and 2. So at this point, you want to pause the video. The solution is in the next page, and we are going to continue. Okay, so when you want to find the integral, we previously also learned that you can solve it not just by hand, but also with Python. So here is the code to do it in Python. Okay, so it's the quad where you put the function here, which is 0.5x, right? And then once you put the function in, you simply say what is the area you want to find. So the area is between 0 and 1. And that's it. If I give you 0.25, which is the same as if you calculate it by hand. So why do we need this probability density function or mass function? Why is that useful? Well, life is uncertain, right? You don't know who's going to win the World Cup, which company would you end up working for? Are you going to have a successful life? There are a lot of things that are uncertain in your life. However, if you can't predict the future, if you could have an accurate likelihood of these things happens, you can still make like really good decisions based on informed likelihood, right? If you're highly likely going to succeed doing ABC, then it makes sense that you pick ABC, right? Or if you are very good at it, you can pick the right stocks and make lots of money, or in general just make good choices in life, right? So much of data science is really about understanding and interpreting this uncertainty. And that's why understanding like how to model uncertainty is really important. Okay? So today we're going to do a little bit more to familiarize ourselves with the basic concepts of probability. Okay. So right now we've looked at single variate, but there are also multivariate probability mass and probability density function. And the way we can write them is like this. So this is an example of two variables. This is an example of three variables. Three variables. Of course, we could end up having a lot of variables. So what we like to do is just write P of x, representing a vector of variables. So P of x is now a vector, which could imply just one, or it could mean a vector of a lot of random variables. Okay. Now, when we write something like this, right, probability x comma y, what does that actually mean? Well, it's when you plug x and y in here, what you're getting and what you're asking for is what is the probability of x and y happening? This is the key. When you plug x and y in here, x and y, right, you are really asking the probability of x and y happening. And this together is called a joint. You're joining them together, right? Joint distribution. So it's not just a single distribution, it's a joint distribution of multiple variables. The notation, right, x and y, can also be written this way. What is the capital P that x happened and y happened? Another symbol for and is this intersection symbol. So this is another way you might see it. Although most of the time, notice how this is so much shorter. So we prefer this notation a lot most of the time. Okay. So if this symbol is intersection or and, if we do the opposite of this with a U symbol, then the logic is or. Then if we write something like this, that is saying what is the probability of X happen or Y happen? which is a different logic, right? This and the A and B is different from A or B. So the OR logic. How can you find the probability of multiple events based on the OR logic? So if we want to find something like this, probability X happen or Y happen, this is actually equivalent. This is equivalent to the probability of X happen plus the probability Y happen minus the probability X and Y happen. So you can kind of understand why this equation is the case through a Venn diagram. So the area, so probability and A or B happen is essentially the area here, right? This is the area. Therefore, if you want the area, you want A, the area of A, and you want the area of B, right? However, notice when you add area A and B together, the center portion where they overlap is added twice. So you have two of them. Therefore, you have an additional area right here. Right? You have that's an extra one. And therefore, you have to subtract the portion where X and Y or A and B happen. You need to subtract out this portion. Then you will get the total area instead of having one additional portion. And that's why the area for A and B, sorry, A or B requires you to have the probability X, probability Y, subtract their intersection. Okay? All right, let's understand this thing, joint distribution a little better. So a joint distribution will look something like this. So if you want the probability of X equals to 0, Y equals to 0, X equals to 0, then the intersection will be here, right? So that will be the probability, right? Or if you want the probability of X equals to 1, Y equals to 1, which would be right here. Or X equals to 1, Y equals to 0, which would be here. Okay, so you can kind of picture if you have two variables, then it will be a table. A three variable, it'll be a cube. Four variable gets very complicated, but this is the general idea of how it works. Now, when we are dealing with joint distributions like probability of x and y, a common question is if you know the probability of x and y together, do you still have access to the individual probabilities, such as probability of x or probability of y? And the answer is yes. And this process is called marginalization. Marginalization. Using the table here, you can kind of see that the probability for example, like we want to find the probability of y is equal to 0, right? We have the joint distribution right here. If we want to find the probability that y is equal to 0, it's simply this part. So it's probability of y equals to 0 and x equals to 0 plus probability y equals to 0 and x equals to 1. So you can kind of see we still have that information. So in order to do this information, what we do is if we're trying to find the probability y is equal to 0, we need to keep probability y equals to 0 and then sum up all the possible x's. So x equals to 0, x equals to 1, and sum them up. And that's why when you're trying to perform marginalization, which is to find just one variable, the equation, if you're trying to find probability x, you are marginalizing, essentially adding up all the y's while keeping x the same. Alternatively, if you're trying to find a probability y, you're adding up all the x's, right? X equals to 0, x equals to 1. Again, you're trying to find probability of x equals to 0, for example, then you got to add up all the y's. Y equals to 0, y equals 1, y equals to 2. So marginalization, if you look at it visually, makes a lot of sense. Like, what is the probability x equals to 0? Well, you just add up all the possibilities. But you need to then convert this concept into mathematics, where equation is that it requires you to add up the other variables. Of course, this is discrete. In a continuous domain, instead of addition, we use this thing called integration. So if you're trying to find probability of x, then you need to integrate all the y's. So here you're summing up all the y's. Here, integration is infinite sum. So it's summing up all the y's here in a continuous manner. If you're doing y, on the other hand, then you have to sum up all the x's. So you have to take derivative integral with respect to x. So that's the concept of marginalization. All right, so over here is an example, right? So if you want to find a probability x is equal to 0, which is just here, very simple. It should be 0.6. You simply add that up. You're trying to find a probability y is equal to 0. Here we go. You should be 0.2. So this marginalization, discrete at least, should be pretty easy. Okay. Like, let's quickly answer these questions. Why don't you pause the video and see if you could do this? Okay. The answer is in the next page, so you're welcome to take a look. All right. So the next concept we're going to cover is called a conditional probability. Let's look at these two situations. What is the probability you're going to have a good date? Let's say you're going on a date tonight. So, what is the probability you're going to have a good date? And then, second question, what is the probability you're going to have a good date given that you'll be talking about your ex the whole time? So, so most people would say that the probability of A would be very different from B, right? So whenever you are given an additional information, it may or may not change your probability, right? So what is the like given that you do something, things could change. So this example shows that the probability of an event can drastically change based on some other given information, okay? And this is called condition and conditional probability. So written as probability of x given, this symbol is given y, or probability y given x. Okay, that's what this is saying. So 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 basically in this case, x is talking about whether you have a good date or not, and then y is the topic you talk about. So probability of x given the topic you talk about. And the situation we're just describing will be the probability of x equals to you having a good date, given you're talking about your x. Okay. The conditional probability is calculated. So when you want to calculate probability of x given y, it is followed by this equation, where you have the joint distribution divided by the marginal. Now, if you just look at this and try to memorize this, it's not easy. However, I want to convince you that this equation is actually very intuitive once you can visualize its actual meaning. So, how do we go about that? This equation is not just some random equation. There's a reason behind this. So once you understand the reason, hopefully you'll be able to like just understand where this equation comes about and can come up with it. Okay. So given this table here, here's the probability of all possible events, right? So here's the joint probability distribution, probability of x and y. Okay. So if you're given no additional information is given. If that's the case, then you have totally six possible outcomes, right? One, two, three, four, five, six. You have six possible outcomes if no additional information is given. So therefore, the total probability is then you add them up equaling to one. That's the total probability. Once again, if no additional information is given. Okay. However, let's say some information is given, such as we know ahead of time that y will equal to 1, right? You are given this information. Well, if that's the case, if y equals to 1 is given, then the total probability of likely events that could happen just changed. Is no, these are gone. Like they can't happen because you already know they didn't happen, right? So these information. Therefore, the total probability that could happen is 0.6, right? You just that's all that could happen, right? So this is 0.6, which is probability that y is equal to 1, right? So that's the total probability. And given y is equal to 1, only these two events could happen. So, therefore, if you want to know the probability of x is equal to 1, right? You want to know this, given that y is equal to 1, right? Then what we need is we want to know probability of this given this happened. Therefore, it's saying that what is the probability that this would happen given y equals to 1 is the total. Okay, so given this, therefore, it's saying that 0.1 given that 0.6 is the total. Notice how this point here is equal to probability of x equals to 1 and y equals to 1 divided by the probability that y is equal to 1. Notice that? And which I have it written right here, right? So that's and therefore noticed this is exactly equal to the equation I just told you. The conditional probability logic is based on the constraint of spaces of potential outcomes, right? Once you have identified the potential outcome that can happen and excluded other ones, then this becomes the total. And when that is the total, this is why you put it in the denominator, because this is the likelihood out of the total. So this is the probability divided by the total probability that could happen. And that's the insight into why conditional probability follows this equation. Okay? So, let's do a quick practice. Like hopefully you can like try to understand this equation given this table here. All right. So, this is probability you're having a good day and the probability you have a bad day. And these are the topics you can talk about. You can talk about X, food, and travel. And given this table, try to answer the following questions. Okay? Pause the video. We're going to the answers are in the next page. We're going to continue. Okay. Okay. So now that we've covered quite a few concepts, let's continue with this thing called the independent variable. Well, we previously talked about the concept of conditional probability. So I said that conditional probability is based on this equation. And we went over the logic of why this equation is reasonable for conditional probability. And once you have this equation, you could actually just move this over here. So now you have P of y. So what that's saying is P of xy is equal to this. Here is equal to this. So this is a simple algebraic manipulation. So you can kind of see that, right? You can see the joint distribution is actually the conditional multiplied by the marginal. So this right here is actually real key. Now, however, if we know that the probability of y doesn't influence x at all. So here's the key, right? Notice how the joint distribution is conditional times the y. Well, this conditional, what happens if y doesn't influence x at all, right? No matter how you change y, it doesn't matter. So, for example, let's say y is that whether it rained 10 years ago on a particular day, and x is whether you're going to kick a rock today. And they basically have basically no relationship with each other. If that's the case, then you can actually cancel this out, implying that probability of x times probability of y is equal to the probability of x and y. And this is how we actually define independence. So probability independence is when the probability distribution of x times the probability of y without the conditional, right? If y influence the probability of x, then the joint distribution has to be written this way. If y doesn't influence x, then adding y doesn't matter. X won't change anyways. Therefore, it's just probability of x times the probability of y. And here we have the equation for independence. So when we talk about two events, x and y, that they're independent, mathematically speaking, it means that when y happen, you know that y happened. It doesn't influence the likelihood of any x outcome. Okay, leading to this definition. This right here is the definition of independence. All right. So when we collect data, we then have this strong assumption we tend to make, which is called the IID assumption. The IID assumption means that the data are independent and identically distributed. Often we collect the data, such as, let's say we collect the blood pressure from 100 people, right? We have 100 people that we're collecting from. And we want to assume that the blood pressure from person A has nothing to do with person B. Like if person A has high blood pressure, person B, assuming they're not related or have anything to do with each other, you randomly pick another person, person B. The blood pressure from A should not influence the blood pressure from person B, and that's what these independence mean. So when we collect data, we like to make that assumption. That's a very strong assumption, implying that when you collect data, you need to make sure person A has nothing to do with person B, they're not related, and nothing to do with person C because of this assumption. Like most of our algorithms has this assumption. Okay. And this is called IID assumption, independent, identically distributed. Okay. All right. So we previously learned the conditional, right? We have this is the equation for the conditional distribution for probability of x given y. So probability of x given y, well, we made the observation that we can move this here. So the join is just equal to this, right? Because we moved this over here. Well, this logic carries over as well. So this is probability of x given y. But what about probability of y given x? Well, it's just the opposite. It's the join divided by x, right? Join divided by y. And we can then move this also over here, leading to this equation. So this is, we're going to call this observation A. We're going to call this observation B. The point is, if you combine observation A and like you have one observation, second observation, if you combine both logic together, right, notice that this and this is the same. Therefore, this must equal to this, right? If if A is equal to C and B is equal to C, therefore A is equal to B. Okay, that's the logic here, right? Once we have that logic, we have this here, and this leads us to two special cases that we call the famous Bayes rule. So this means that if we just move probability of y here, right, then we have probability of x divided by uh, x given y is equal to this equation. Conversely, probability y given x is equal to this equation. So this right here is Bayes' rule that came from the conditional probability distribution of observation A and observation B. Okay? And this Bayes rule turns out to be very, very important because it forms the foundation of statistical machine learning, where we often plug X into some kind of model, right? But the model is probability Y given X. So the output will tell us, well, what is given X, what is the likelihood probability Y equals to 0, Y equals to 1, so on and so forth. It basically tells you the likelihood of events happening. And in statistical machine learning, you are given some kind of input, and the output is the probability of various outcomes, like such. Okay, so this is the equation for Bayes' rule, and now we're going to practice using it in a neighborhood where 90% of the kids are getting sick due to flu. So probability of flu is 90%. Probability of measles is 0.1%. The probability of observing a rash given the kid has a measles, so rash given a measles, is 0.95. So, given these, what is the probability that a kid would develop a rash and have flu? Okay. Second question, develop a rash and have measles, or develop a rash or have flu given a rash. Okay. Pause the video. We're going to continue. Okay. The solution is also in the next page, if you can see it. All right, so now that I've convinced you why knowing the PDF is really important, we want to talk about a little bit about visualization. We want to, it's important, and given some data, we want to get a sense of what this probability distribution look like, right? And the most easy and the basic way of visualizing it is called histogram. There are many other ways here, which we're going to learn a good deal of them. But we'll learn the easiest one first, which allows us to essentially visualize it. And the idea of histogram is really simple, right? So, what histogram does is that you are simply, let's say we have this data set, it's only 4 samples. And what we do is when we observe the first one, we put a block here. So, we put a block of 1. And then we see the second one. We put another block of 1, stack it up. And then we put a third one, right? So we put a 1 here and a fourth one. So this right here basically is the histogram. So if you collect the data, you can essentially use this code, like drawing, PLT hist, to draw the histogram, and it will tell you the probability of events happening. Now, this right here is giving you count. It's not giving you probability. You can essentially reset it this way. This will give you the probability. So it's telling you like 50%, 25, 25%. Okay. So this is the code on how you can create this visualization. Or if you have some data that's much, much larger. So I generated some random data. You can see random. And then once I generated this random data, once again use the histogram command. Now, this first one is the histogram command. And basically, I put the data in. And 20 here is saying that I'm splitting it into 20 blocks, right? You can make it thinner or fatter if you want. And this face color, blue, is just saying I want a blue color with a little lighter blue color. That's all. And then this just shows it. So this is how you basically visualize a probability distribution, because events that are happening a lot will stack up higher, right? If it happens a lot, then each time it happened, you'll stack up. And the events that didn't happen very much would just stack up shorter. And therefore, you can see that around 0, right, the probability of things happening in this region is pretty high. And the probability of things happening in this region or this region is pretty low. So you can get a sense of the likelihood of things happening. And then you can say that, well, probability of 5 is basically 0, right? Because it's probably not going to happen. Okay, so for your next practice, what we want to do is go to the course website and find these 3 files. And I want you to practice generating the histogram for each of them, and then see if you can calculate the average, right? And calculate the probability that someone score higher than 1300 on the SAT. So this one was the SAT score. And then you want to calculate the probability that you have to wait more than 3 minutes. So this one is how long you have to wait in line for lunch. So you want to calculate the probability that you have longer than 3 minutes, or calculate the probability that someone is younger than you. So this is the age of random student at the university. Okay. Okay. So hopefully you can do this. We're going to continue. Okay. So one of the most important distributions you're going to learn is called the Gaussian distribution. This equation is so important, I expect you to memorize it, at least for the exam. Okay, so it's also known as a bell curve. The Gaussian distribution is so important because it's used to measure the majority of our science distributions. Like, yeah, the majority of our science distribution basically is a Gaussian distribution. Can be shown that it becomes a Gaussian distribution. So if you fall in the center, that means you're like the majority of the people, right? And if you fall in the side, then you are the minority. Okay. And majority, 68% specifically, falls within the first standard deviation, which is from this point to this point. So 68%. So so this is basically how we measure the population very commonly. And another name for the distribution is called normal distribution. So Gaussian normal, they're the same thing. Now, if you want to calculate the probability, like I said, you need to find the integral, the area between like a point A and point B, right? So that's how you want to solve it. And therefore, you need to find the integral because this is, after all, a continuous distribution. So solving this integral is not fun. Like you don't want to be solving this integral. So what we have done, like historically, or at least when I was learning it in the 90s, when I was learning Gaussian distribution, we basically had this thing called the lookup tables on a book. So we had to go to a book and then flip to the point of this CDF function. The CDF function is this idea where if you it's a function where if you plug b value in, it gives you the area from negative infinity to b. So let's say we have this distribution. So if you plug b here, it basically gives you the area to here. So this whole area. So it's a function that gives you the area. Okay. So if you plug b into f of b, it will return the area. So long story short, I basically when we want to know the area to b, or we want to find the area between a and b, then we have to find the area of a and then the area of b. And if you find the difference between them, that gives you the area in between, like such. So I had to like look up in the table and see what area to B is, area to A is, and find the area in between them. So that was what I had to do in the 90s. Um, Back then, Python didn't exist. So we had to like carry this book, which was not fun. But lucky for you guys, now you guys can just use Python and it will solve it for you. So how do you go about using Python? Well, like I said here, if we look at the figures below, let's look at the figure. If we find the area B here, right? So if we plug f of b in, that will give us the area here. And then if we find f of a, which is from -1, so let's say we're trying to go from where we're going. We're trying to go from -1 to 2. So we are trying to find this area. Okay. So if we find a, which is -1, this is A and B. So if this area subtracts this area, notice how the difference between them is the area in between them. Okay. So you just nowadays you just have to call the Python code. Here it's called the CDF. CDF is essentially this capital F function. And you plug in the location, which is -1 right here, right? -1. And then location and scale tells you where the center of the distribution is. So the mean is around 0, right? So I put 0. And the standard deviation here is just 1. So I put 1 here. Now you calculate the CDF for A and B, and then you can get the values, right? You can get the value for A and the value for B. And once you subtract B, A from B, you'll get the area. So it's essentially saying that this area here is actually roughly 82%, right? You can get more documentation here if you're looking for it. So that's the idea is really simple. Like basically you have this distribution, Gaussian, and if you want to find the area in between, you just find the area all the way here and subtract the area all the way to here, and that will give you the area in between. And you can use this to really easily get it for you. So that's to find the area. But what if you want to do the opposite? So what if you know the probability and you want to find a location? And that would be called the inverse. And why would you might be wondering, like, what kind of answer questions can we answer with that? The inverse CDF allows us to answer questions like, well, if you want to score higher than 90% of the students on the SAT, right, then what score would you need? Like, that would be an example of a question you can answer. Or you want to say 5% of the score students score higher than you, then what's your score? So notice previously we plug in the score for the SAT. We can plug in the score for the SAT like here, and then you'll give you the probability. Now we have the probability and we want to know the score. You see how like you're doing backwards, okay? And to do this is actually very easy in Python as well. Instead of CDF, it's called a PPF. So over here, it's saying that PPF at zero point 0.5, so half of the area. I want you to tell me where half of the area is. And you can see, since the center is at 0, half of the area gives you 0, which is here. Or you want to say 95% of the area, which is here. And therefore, it's saying that it's roughly 1.6. That will give you 95% of the area. Okay? All right, so let's do a quick practice with the inverse CDF. Given the SAT score here, right? So the mean is 1,000 and standard deviation is 200. What score would you need to achieve in order to be the top 95 percentile? Okay, see if you can solve that 95 percentile. The answer is in the next page. So pause the video. Here's the answer. Okay. Apparently, you need 1328 to be the top 95 percentile. Okay, let's now practice your understanding a little bit more. Here is this is actual data. Height of adult man in United States are approximately normally distributed with 70 inches of mean. So an average male is 70 inches and a standard deviation of 3 inches. And an average female is 64.5 inches and a standard deviation 2.5. Okay, now let's use what we learned so far. Power your laptop with NumPy and see what percentage of the male will be taller than 5'7". Okay, so what percentage will be 5'7"? Second, what percentage of female will be shorter than 5'7"? Okay, now in another one, in an imaginary world where a woman would never play chess with men shorter than them. So woman would, in this world, they won't play chess with men that's shorter. What height would men need to be to play chess with 90% of the female population? So this is a more complicated. You have to kind of think through this, how you would solve this problem. Okay, and pause the video because like I have the solution here. All right, so besides Gaussian distribution, here's documentation for a bunch of other distributions, right? We're gonna learn later. And besides we learn the CDF and the PPF, right? So that CDF is how you find the area. PDPF does the inverse of area, and then there's the PDF, which gives you the actual result. If you plug X in, it actually gives you the output. Okay, the documentations are here. When you have a chance, if you're stuck, this is what you want to look over. All right, here's the very last exercise. This is a visualization exercise. I want you to draw this picture. Now, I know like if you haven't had a lot of practice, what you can do, you can just look over the code and see if you can reproduce it. Or you can give yourself a challenge and see if you can do it without the code to help you. Okay, I think that is it for today. So I will see you in the next lecture.